Good evening, and thank you for inviting me to present at this workshop. I'm Ganesh Pai. I am a principal researcher at KBR and a contractor member of the scientific staff at NASA Ames Research Center in the robust software engineering technical area of the Intelligent Systems Division. I am delighted to be able to present some exciting work that our group is doing on trusted autonomy. This is joint work with Ewan Denny and others in our group. First, I'd like to spend a few slides talking about the motivation for this work and how it has evolved from our early thinking on the topic of dynamic assurance, especially with the introduction of autonomy and autonomous capabilities into the mix. Then I'll give a high-level overview of our concepts for dynamic assurance, touching upon the tool support infrastructure that we're developing, after which I'll give an example of how we have implemented and applied these concepts on a concrete platform. I'll conclude with the challenges we've encountered and how we plan to address those challenges. Safety-critical systems evolve through their life. In effect, the assurance case that we create at the time the system was approved will need to be kept consistent with the system as it currently is in operation. Thus, the initial motivation for our work was to evolve both the system and its assurance case in tandem. About half a decade ago, we proposed the idea of dynamic safety cases that would be driven by three main principles. First, to proactively update assurance reasoning and assess the extent of confidence provided. Next, to increase the level of formality in the assurance infrastructure to support increasing automation. And third, to admit both human action and automation-based updates. The main assurance artifacts that were the target of the updates were structured arguments, such as those created using the goal structuring notation and the claims arguments evidence notation. The figure on the right shows the lifecycle for dynamic safety cases, which is based on 4 continuous activities. A key insight we've gained from this early work is that it is useful to distinguish and characterize the static and dynamic aspects of assurance. Conventional assurance cases and underlying arguments are traditionally created and evaluated at design time. Design assurance thus sets a baseline for what constitutes an acceptable level of risk, and this is effectively static. In operation, the objective of assurance is to maintain this risk at an accepted level as there are changes to the environment, possibly to the system, and in turn the extent of assurance in a particular system capability. This is runtime assurance. Thus, although it is possible to update arguments during a mission, and possibly in real time, it makes more sense for these artifacts to be updated over a longer time interval, that is between missions, or when there is an appreciable change to the system that requires a reassessment of the baseline for acceptable risk. At the same time, we need a different mechanism to assess whether or not there is sufficient assurance during a mission. So if required, some mitigations can be invoked to maintain risk at an acceptable level. This necessarily involves some machine processability, and we believe this form of assurance should be in a computable form. This could be as a quantification or as a formal logic, and we're currently looking at quantification. Collectively, this notion of static and runtime aspects of assurance, which are both updated at different intervals, is what we consider to be dynamic assurance. We'll now consider assurance of autonomy, in particular systems where autonomous and automation capabilities are implemented using machine learning-based components. We can characterize the challenges that emerge along several dimensions, some of which are listed here. For example, the learning scheme, or whether the learning occurs offline, online, or during the life of the system, how autonomy is implemented, and so on. The specific assurance challenges have by now been reasonably well documented, so I won't go over those again. But for this talk, the focus is mainly on machine learning components that have been trained offline in a supervised learning scheme. And the paradigm that we're interested in is one where the learning component is deployed, then retrained using in-service data, and then redeployed sufficiently frequently, perhaps once every few months. And at least one major electric car manufacturer already does this with their over-the-air software updates. Our concept of dynamic assurance is underpinned by 3 main notions. The notion of an assurance measure is to build an abstract probabilistic model of the system behavior focusing on specific quantifiable system and component properties that are associated with dependability attributes and functional capabilities. The second notion is that of an integration architecture, and the objective here is to answer what we can do with quantified assurance to ensure that the accepted level of risk is maintained. In other words, how can we use assurance measures for intervention and recovery, and in effect make decisions under uncertainty? And lastly, we have the concept of a dynamic assurance case, which ties design and operational assurance together as a multi-perspective model-based risk management artifact. The vision here is to provide an integrated concept of assurance which is suitable for both machine consumption and for human stakeholders, which would involve regulators, operators, managers, end users, and so on. In the next few slides, I'll go into some more detail on each of these concepts, but in the reverse order. As a quick reminder, a safety assurance case is a comprehensive risk management artifact, and the various characteristics of a safety case have been listed here on the slide. I won't go through them all. Instead, what I will now discuss are what we think are the core components of a dynamic assurance case, and this has been informed by our experience in creating safety cases that have been successfully evaluated by the Federal Aviation Administration and also within NASA for supporting missions under the aeronautics programs. For example, the UAS Traffic Management, or UTM project, as it is known here in the US and in some other countries. Assurance policies provide what we call an assurance basis. Concretely, it expresses what assurance means in terms of the conditions under which assurance is impacted and the associated risk mitigation requirements. In our tool implementation, we have implemented this using tabular models as hazard logs and requirements repositories. Next, an assurance architecture models the system from an assurance viewpoint as a collection of scenarios that show how risk is modeled. And this can be seen as an implementation of assurance policies. And in our tool realization, we compose barrier models, each of which represents a specific risk scenario. Assurance is underpinned by the evidence model, and in part we can specify this from assurance policies. In our tool, this is an interface to external evidence items such as verification and validation results, operational data, and so on. And this model gives us a tool for evidence management and in turn for configuration control of the assurance artifacts. As previously mentioned, the quantification models are a probabilistic abstraction of system behavior, and we can use this to both establish a baseline level of quantified assurance and then evaluate in operation whether or not there is a deviation from that baseline. And effectively, this is a means for runtime risk assessment. We'll discuss this more in the next few slides and see how quantification models are very closely connected to assurance measures. And lastly, assurance rationale ties everything together, capturing various kinds of reasoning. For example, whether there was sufficient coverage of hazardous scenarios, whether the assumptions made for quantification were reasonable and valid, and so on. As I mentioned, we'll focus on the quantification model for this talk, and at the end of the talk, I've listed some recent publications that develop the remaining concepts in more detail. Our methodology for developing quantification models and in turn assurance measures comprises three broad steps. First, we specify measurable assurance properties based on the concept of operations and various system descriptions, focusing on dependability attributes or functional capabilities. And an assurance property is basically a probabilistic or logical characteristic associated with either a dependability attribute or a functional capability. Our next step is to build a stochastic process model of the required behavior of the system. And we think this is reasonable because many safety-critical autonomous systems are stochastic dynamical systems. In our implementation, we're admitting different kinds of discriminative and generative models. So we've experimented thus far with dynamic Bayesian networks. We can build these models either using elicitation techniques or by transforming a formal system description or applying statistical techniques to execution traces and simulation runs from models and prototypes of the system, or a combination of these three. And lastly, we map the assurance properties to the random variables of the stochastic process model. Then, to determine the extent of confidence in these properties, we propagate uncertainty through the model and query it for the posterior distribution of the corresponding model variables given runtime data. In effect, the executable stochastic process models are what we call assurance measures, and they represent an abstract reference model for the system. Here we're showing a proposed architecture for trusted autonomy that integrates assurance measures. A collection of runtime monitors assesses system properties, taking inputs from the environment and the system state. And these runtime monitors may also monitor assurance properties. The assurance measure quantifies confidence in these properties using both the inputs and the outputs of the monitors. And then this is fed to a decision-making mechanism that determines whether or not to proceed with the nominal system operation or to invoke contingency management actions. The architecture is closely related to the simplex architecture and its variants, but we view it as providing an additional level of analytic redundancy that is somewhat wider in scope than traditional simplex. When seen from this viewpoint, assurance measures can be considered as a form of data fusion, aggregating information from the runtime monitors, from runtime verification mechanisms, and other sources. But the key point here is that the output is an assessment and forecast of confidence in the property. So putting it all together, our methodology for dynamic assurance looks thus. Firstly, we assume that the autonomous system in which we want to develop trust is described using, for example, the concept of operations or a physical and logical architecture. We're also assuming that there are other runtime monitors in the system, and some of these are part of the system requiring assurance, and others may be tied to the validity of the evidence items that are part of the wider assurance case. Based on this, from a system focus, we will firstly develop the static elements of the dynamic assurance case, and this forms part of design and development assurance. In effect, this entails developing and instantiating the various components as shown, including the hazard log, the assurance requirements, developing an assurance architecture, capturing the assurance rationale, and so on. We compile the quantification models into an assurance measure that we then integrate into the system architecture. And because this represents a modification of the system, we need to additionally develop integration-focused assurance artifacts that are listed there. Then dynamic assurance, which is the runtime assessment of confidence in assurance properties, can then be used either actively or with the decision mechanism to trigger some contingency management actions, or passively displayed on some remote dashboard to some system operators. For example, the remote pilots of a fleet of unmanned aircraft systems or air traffic control. Next, we'll look at where we have been applying this concept and an illustrative example. At the moment, the work is being conducted under NASA's system-wide safety program and also under funding from the Assured Autonomy program of the Defense Advanced Research Projects Agency. We have been applying it to both aviation and maritime platforms to a variety of use cases, spanning the whole gamut of learning schemes and diverse application concepts. And for this talk, I'll mainly present our work from the aviation domain, in particular for runway centerline tracking. And effectively, this is a specialized perception and control problem. The application platform is a certificated engine, a single-engine fixed-wing aircraft system that our aviation domain collaborators have modified to be remotely and autonomously piloted. In other words, the overall platform includes a flying aircraft and an Ironbird test rig, which is a hardware-in-the-loop simulator. And at the moment, we have applied the work to the Hill platform, and our plan is to apply it then to the flying platform. The concept of operations involves taxiing on the runway or taxiway while following the center line. This is a simple scenario to start, but it can be scaled up for taxiing for takeoff, or the landing roll after touchdown, and in general to taxi operations in the airport environment. The autonomy pipeline consists of a wing-mounted camera pointed to the nose of the aircraft, which feeds runway images or scenes to a deep convolutional neural net, the outputs of which are estimates of cross-track error and heading error. Cross-track error is essentially the perpendicular distance between the roll axis of the aircraft and the center line, measured at the nose wheel. And then heading error is the angular distance between the compass direction in which the aircraft nose is pointed and the compass direction of the runway. These estimates are then fed to a PID controller, which provides steering and actuation to control the aircraft movement. As shown, the main taxiing requirement is not to exceed a defined lateral offset from the runway centerline, within a certain level of confidence. And the associated safety requirement is to not leave the runway pavement or the side stripes, a hazardous consequence known as a lateral runway excursion. This chart shows the integration architecture realized for this platform, along with the autonomy pipeline components and other systems required for aircraft movement. As previously mentioned, the integration leveraged a hardware-in-the-loop simulator, so our assessment and assurance is in principle of the simulator. The actuation is achieved in hardware, and these are converted into actuation signals that are fed to the X-Plane software simulator, which in turn simulates taxiing, aircraft movement, and the camera images that are ultimately fed to the deep CNN component. Our quantification model is a dynamic Bayesian network, and here we're showing two adjacent time slices. Although the network would be unrolled for an amount of time steps representing the duration for which assurance forecast is sought. This parameter could be determined, for example, from the dynamics of the aircraft and the characteristics of the runway. In the model, the parameter D represents a runtime monitor, which determines whether the images that are seen are representative of the training distribution for the CNN and the data set that is used to build the quantification model. HE sub E and CTE sub E are the random variables for the estimated heading and crosstrack errors produced by the deep CNN. CTE sub A is the true crosstrack error, which is uncertain. And the properties for which assurance is sought are as shown by the formulae. And for this application, we used two values of offset, set at 1.43 meters and 2 meters. Effectively, this model shows the time series evolution of crosstrack error, with its value in one time slice being determined by the true and estimated values of crosstrack and heading errors in the previous time step, as well as the images in the current time step and whether or not that image can itself be trusted. I won't go into more details on this model and how we built it here, and for more details, I would recommend that the audience see our SafeComp paper, SafeComp 2020 paper, which we will present in a couple of weeks from today. For integrating the assurance measure into the system, we've also designed a simple decision-making mechanism as a proof of concept. This mechanism signals a contingency manager based upon the aircraft state, the history of the assurance measure for a number of time steps, which is a conservative estimate of the time the aircraft would take to laterally depart the runway given simplified aircraft dynamics and that it has violated the taxiing requirement. We also implemented a user dashboard, which is shown here on the right, that displayed the assurance forecast for the current time and for a look-ahead time, shown here as a probability density map overlaid on the grid of the runway. So going from left to right and vice versa means that the aircraft is drifting laterally, and going from bottom to top represents forward taxiing motion. We discretize the runway by time steps and crosstrack error relative to the runway centerline, and each cell and its color shade indicates the probability mass that the aircraft is at a given location on the runway at a given time. Darker shades indicate more certainty and lighter shades indicate more uncertainty. It's important to note that we do not estimate the true crosstrack error from this model, but we only quantify how confident we are that the aircraft is situated at a particular location at a given time. The decision mechanism then is simply that if the probability of violating the offset is greater than 0.3, then the aircraft has violated the taxiing constraint, following which we either slow the aircraft down or stop if the violation exceeded some defined time durations. Next, I'll run a simulation video. Here we see the assurance measure and contingency management in action in a simulation of taxiing under overcast weather conditions at a certain time of day after the CNN was trained for a different time of day and weather conditions. So let me scroll this back a bit and then try and talk through what's going on. So initially we see that the assurance measure is reasonably confident of the true aircraft location shown here by a black line. So if I scroll further on, a black line right there becomes a little more apparent. So since this is a simulation, we had access to the simulation parameters, and that represents ground truth. So here we show it as a simple validation. Then, as the taxiing continues and the aircraft suddenly enters an intersection, we will see that the CNN becomes uncertain, and so does the assurance measure, and the contingency action then switches from taxi to slow to stop, and eventually the aircraft comes to a halt. And that contingency action can be seen, for example, by looking at the aircraft status traffic light, where you see it has switched from green to orange to red. And the main takeaway here for dynamic assurance is in the sense of runtime estimation of confidence in the assurance property. The ideal response we would have expected from the aircraft would have been to stop sooner or to slow down as it approached the intersection. But in this case, the behavior is explained since the contingency action is only triggered after assurance has been lost for a certain amount of time. Next, we would like to move to a system where the contingency action is based on an assurance forecast and on history. However, that is still ongoing work. We're implementing many of these capabilities for dynamic assurance in our toolset Advocate, which also provides capabilities to create the static aspects of the dynamic assurance case. And here you see some screenshots of dashboards, the various assurance artifacts, and how its model-based implementation facilitates traceability and consistency. There are a number of other elements that have not been shown here, such as the evidence model, as well as other infrastructure elements for automation, such as querying, pattern instantiation, preliminary quantitative risk analysis, and various views. The tool is dashboard-centric, and we provide analytics and process views to both steer the development of the assurance case and to track progress and performance. We're working on additional capabilities, including a suite of domain-specific languages, which collectively form what we call the structured assurance language, by which we aim to formalize and support analysis such as domain modeling, consistency checking of the arguments against the domain models, and then synthesizing some well-formed arguments. What I've presented thus far represents our current steps in developing a dynamic assurance framework for ushering in trusted autonomous systems. However, many challenges still remain, which are on our roadmap for next steps and future work, and some of these challenges have been listed. We want to investigate the principled ways to develop the decision-making mechanisms that are required for contingency management, and we want to take uncertainty quantification from the assurance measures into account. We want to further explore how the various assurance measures should be best aggregated, recognizing that these relate to dependability attributes and that there are trade-offs involved in balancing these attributes. We additionally want to more tightly integrate assurance measures and into the remaining assurance artifacts, in particular the architecture. The autonomy paradigms, we think, pose the more fundamental challenges, especially in evaluating how our approach applies to reinforcement learning based components and how they will apply when we transition to online learning. Ultimately, the broader goal of this work is to support certification processes. And by that, we mean the regulatory aspect of system certification, which is substantially broader in scope than the software aspects of certification, which we also want to support. Tool capability enhancement is a major component of our research roadmap, and we want to enhance the capabilities of our tool to integrate domain models, for example, ontologies. I previously mentioned that we're developing a suite of DSLs that are part of the structured assurance language, and we want to extend the concepts of modularity and hierarchy across the various assurance artifacts, and this is yet another aspect of our outlook to further enhance the toolset. As I mentioned, here is some work that was used to formulate this talk, and that is the end of my talk. Thank you, and I will take any questions you may have now.